as I say, climate change is a difficult topic because it's so complicated. It's very, very complicated. It's a very, very complicated science. It's you're talking about a very, very complex process. It's very, very complex, and you're talking about something that people don't really understand very well. When you're talking about general physics, you know, we can understand the behavior of atoms, electrons, there's quantum mechanics, there's a lot that we don't understand, that physicists don't understand, but there's a deep understanding to the molecular, to the subatomic level how particles behave, for example. But in a complex system like the Earth's climate, it's absolutely, to really understand what's going on, it's very, very complicated. And one of the things that what I'm trying to do in these lectures is just give you, you're not specialists, I'm not a specialist, but we have to have some knowledge about this. We have to understand something about this so that when we see people talk about it, we have to have some idea whether they're actually speaking nonsense or whether they make sense. And the thing that you'll and one of the messages that I want to give you here in that regard is that most of what you hear, and that's on both the extreme sides, is nonsense. It's because there's such a political. There's so much at stake here in terms of political and economic power that people are making statements that really have very little to do with reality. And so you have to be very, very careful, and you have to see what people's motivations are that are making certain claims. What we'll see is, in fact, the reality is that it's very clear, or it's very, very, very likely that the humans are causing an impact by increasing carbon dioxide in the atmosphere. What I said the last time, that a doubling of CO2 will produce in the absence of feedbacks about 1 degree Celsius increase. That is, I think there's no doubt that that is what's going on. There's no doubt that there's. I think it's absolutely 100% that there's some impact. It's also a probability greater than 0 that it could be a major impact. But it's also a probability greater than 0 that it could be a very great negative impact. It's also probability greater than 0, and also not a small probability that it could be a relatively minor impact, negative impact. And so when you consider a world where most of humanity still is underdeveloped, billions of people still don't have electricity, they don't have sewer, they don't have clean water, billions of people don't have clean water, adequate. Large numbers of the human population still don't have adequate food, and as well as access to inexpensive energy relative to their income. You have to start weighing what is the impact of and how much you do given the uncertainty. And I think that's a very fair question. And at least for someone like myself coming from the West, when you read, for example, in my country, people think, well, we've got to, and especially the Europeans, that they say you've got to get out there and make do all this to reduce the amount of carbon dioxide in the atmosphere. Well, there's billions of people that are not enjoying the benefits of the economic development that created that. So I think that's a very legitimate question. So I'm going to finish up this presentation today by talking about we're going to finish the talk on the climate feedbacks, I believe I was starting to introduce the concept of feedbacks, climate sensitivity, that is, what is the expected effect of an increase in the Earth's surface temperature from a doubling of carbon dioxide. That's the typical definition of climate sensitivity. Then I'm going to go, and this is much more brief than I would have liked, but as I was looking at this material, it's just very complicated, and I think it's beyond the it's beyond this this class in terms of what can be reasonably presented. But I want to give you a flavor. I want to give you a flavor of what's out there, and basically the message that I want you to take away, and it's really very clear, is that there's a great deal of uncertainty. And the reason, and that uncertainty will explain, I think should clearly explain to you why people are not rushing out to make major changes in the world economy and major changes in the way that we organize ourselves in terms of economic systems in order to potentially change this. And the reason is because there is a great deal of uncertainty. There's no other, there's a great, given a great deal of uncertainty, there would be winners and losers, and the fact is that the winners would be the winners now. The people with money would end up have more money, relatively more money and more power, and those that don't have money and power are going to stay poor, and that's the reality. That if that you basically would be freezing in place the current distribution of income. So what I'm going to say is that at least the possibility, to talk about the possibility that climate models are overstating potential warming impacts. That is something that's a real controversy right now, is that these climate models are over-predicting the observed temperatures. I'm going to talk about my own view, and this is something that certainly I'm going to talk about something that I've observed 10 years ago, but it's also, personally I'm challenging myself to some degree. My own view is evolving as data comes in. I think it's my own view, and I'll state this, I think there's definitely some feedback effect. I think that the data suggests some feedback effect, but whether it's enough to warrant major action is not clear. That's my view. We're also going to talk about some of the data about the greenhouse gas emissions by region of the world, so you can see, well, who produces it and who is going to produce it. What parts of the world are likely, as they develop, are going to produce more greenhouse gases. And so what we want to think about in terms of, well, what parts of the world would need to develop, and what's going to be that impact. And finally, I'm going to spend a lot of time talking about the generation of electricity. Electricity generation represents about 30% of the use of energy. But the thing that we've talked about this semester is the importance of electricity. Electricity is an essential part of the modern industrial economies, and I've really made the use of electricity and the impact of electricity on modern economies is enormous. Basically, electricity from the development of electronic communications in the mid-19th century, the real beginnings of the harnessing of electricity by humans. It's had a major impact. So I think it's very important to look at the generation, how electricity is generated, and how that by a number of countries, we're looking at European countries, China, India, the United States, to get a feel of how electricity is generated. So to see, well, and what are the real opportunities to move to renewable energy. And I think the answer is it's real early on that. So let's get started. We'll begin by talking about the climate feedbacks. I discussed the last lecture that water vapor is the most important greenhouse gas. That is talking about carbon dioxide, but really water vapor is the most important by far. And we talked a bit about how the warming of the atmosphere as a result of an increase in atmospheric CO2 produces an increase in evaporation of water. So there's increased evaporation because there's more heat energy on the water, producing more evaporation, which produces an increase in atmospheric water vapor, and a further increase in surface temperature as a result of the initial increase. That's what's known, that amplifies, known as a positive feedback. And that is, water vapor acts to amplify the initial increase in temperature as a result of the increase in atmospheric CO2. That's the most important thing when we talk about, you cannot overemphasize when you talk about climate change that this is what we're really talking about, is the effect of increased atmospheric temperature on increased evaporation and increasing water vapor in the atmosphere, and the feedback effect of that. That is the most important issue when we talk about climate change. So that's what you should focus on when you see anybody write about this and write about climate sensitivity. This is the issue. What's the impact of increasing water vapor in the atmosphere? And what's interesting, and according to this, according to the textbook that I used to prepare this lecture, the location of the increase in water vapor in the atmosphere matters as well. And this person notes that if the increase is concentrated in the upper portion of the troposphere, it will produce a greater warming than if the same increase in water vapor is concentrated in the lower portion of the troposphere. And if we go back, let me just go, and that's because, if you recall here, the most important things that happen is the net radiation at the top of the troposphere, which is called the tropopause. So the tropopause is that place where where the radiation, the change in radiation has the biggest impact. So if there's more water vapor concentration that increases higher up, then that has more of a feedback effect. If that effect of the increase in water vapor is lower, then it's effectively a negative feedback effect relative to the location of water vapor higher. So that is, and that gives you an idea of how complicated this is to really understand what is happening in the atmosphere. And it's not just the increase in water vapor, but where it's concentrated in the troposphere. So the second thing, talking about water vapor, well, it's very closely connected with water vapor, are clouds. Clouds, very, very important part of the feedback process. And we say likely play, and by likely we mean it's actually still quite, there's a lack of knowledge. We don't really know how to say precisely, or even with any rough degree, whether clouds ultimately act as a positive or negative feedback is still uncertain. Depending upon the nature of the resulting change in clouds as a result of an increase in atmospheric temperature, clouds can produce either a positive or negative feedback. It could be positive or it could be negative. Well, that's how, it doesn't get any more than that. And the reason is that clouds can either cool or warm. And the first thing is that clouds cool the Earth's surface by reflecting sunlight. So clouds are and the ability of the surface to reflect what's called incident solar radiation, that is shortwave solar radiation reaching some surface on the Earth, whether it's the clouds, the atmosphere, or the actual surface of the planet, is called the albedo. So the albedo is the reflectivity. So the higher the albedo, and albedo is between 0 and 1, the higher the albedo, the more reflective. And if some surface reflects incident solar radiation, then it's as if it never came into the atmosphere. It's as if it didn't exist. in terms of affecting the amount of heat in the atmosphere. It's literally, it's like it didn't happen. And snow, fresh snow, is the most highly reflective, and it can be up to 90, between 0.8 and 0.9, the albedo of fresh snow. Now we're talking about, in talking about clouds, and you can see we've got sand. Dry sand is relatively high, wet sand is lower, dark wet soil is the lowest, forest is quite very low. Forest, meadows, these are all relatively water. You see how low water is? So that means the oceans don't reflect, they absorb. Okay, so if you have, but look at these clouds. These are all stratus clouds, altostratus, these are cirrus, these are high clouds. These are low stratus clouds. Those are low clouds. Those are closer to the Earth. And then cumulus stratus are the high clouds that are associated with thunderstorms. So those are higher, and the tops there's a lot of ice at the top, so that makes them more reflective. It's almost like snow. So you can see clouds in general. All of these clouds are more reflective than anything else. So these would be the things that would be underneath on the surface: dry sand, desert, forest. If you have an increase in temperature, as I say, the cooling effect of cloud cover depends upon the difference between the surface and cloud albedos and the amount of incident solar radiation. So it depends on where and when the clouds occur. Let's say if it's in the tropics, for example, let's say that an increase in atmospheric temperature causes an increase in clouds in the tropics, and particularly these kinds of clouds over the ocean, because there's a lot of ocean water at the tropics. That's very dark, so that could have a negative feedback effect. That could have a negative feedback effect. So, but it's more complicated than that, because they can also have a warming effect. Clouds also exert a warming effect. That is, clouds have a warming effect because they absorb infrared radiation emitted by the surface and emit a smaller amount of radiation. So what happens? A cloud absorbs long-wave solar radiation that is emitted by the surface, and it emits solar radiation at the top of the cloud that is colder. The top of the cloud is colder than the Earth's surface, so it has that's a greenhouse effect. That is a type of greenhouse effect. So the net warming effect of clouds depends on how high the clouds are. So high clouds tend to have a net warming effect, while low clouds tend to have a net cooling effect. And particularly, you think about a cloud like you see like the very thin clouds that you'll see in the sky. You think that those aren't very important clouds because the sun shines right through them. They're actually quite important in terms of of surface temperature, because they actually have more of a warming effect. They actually tend to have a warming effect where thick clouds will tend to cool the Earth, and especially cumulus stratus clouds. The cirrus clouds and altostratus clouds, well, especially these cirrus clouds, actually have a warming effect. So if the increase in clouds, so what this means is that it depends on what kind of clouds. What kind of clouds increase, where the clouds are located, all of these factors. For example, if you had an increase in cirrus clouds, say in a desert, let's say in a forest region, in the northern hemisphere, then that would tend to have a positive feedback effect. That would be to increase the temperature. Whereas if you have an increase in stratus clouds, low stratus clouds in the desert, that's going to have a cooling effect. So it's very, very complicated. We're talking about a very, very complicated impact, and the increase, the net feedback effect of clouds remains uncertain. And if you look at this, the potential of clouds, there's a potentially large impact. It's not small. It can completely cancel out. It's possible that the increase in clouds could completely, of the right kind of clouds, could completely cancel out the effect of any feedback effect of CO2. So that's, and that contributes, that uncertainty contributes greatly to the uncertainty surrounding the total feedback effect from an increase in atmospheric CO2. I can't overemphasize that. If you ever look at this, that's one area that you have to keep in mind, is the impact of clouds. A couple of other things that points I will make is atmospheric temperature structure also matters. The air temperature tends to fall with increasing height from the Earth's surface. So as you go higher up, the temperature is lower. The rate at which it declines is called the lapse rate. And it's possible the lapse rate may change as the atmosphere warms from an increase in atmospheric CO2. So because of the increase in CO2, it could be the change in water vapor, whatever that's going on. If the lapse rate decreases, then the temperature decreases more slowly with height. Then that would mean the upper troposphere would become warmer. And if it's warmer, that means there's more radiation going into space from the troposphere. So, and from the tropopause. If there's more radiation, if it's warmer, if it becomes warmer up there, there's more radiation going into space, which means it's having a net cooling effect. That may seem counterintuitive, but when you think about it, you're talking about there's more radiating. Whereas if the lapse rate, where the lapse rate to increase, then the temperature would decrease more rapidly. So if the temperature falls more rapidly as a result of an increase in CO2, then that would be a net positive feedback effect. Again, very complicated stuff. This is stuff that can happen, and the important thing here is these are instantaneous impacts. As the amount of CO2 in the atmosphere increases, these are immediate. They have an immediate impact on what goes on in the atmosphere. Change in the extent of ice and snow, of course, a reduction in sea ice would reduce the albedo, and that would result in a greater absorption of incident solar radiation. For example, the reduction of ice pack in the Arctic has had some impact of reducing albedo during the summer months in the Northern Hemisphere. No question about that, and that is some type of positive feedback, and that's it's also possible that change in cloud cover could take place as a result of a reduction in sea ice, and that change could produce a negative feedback. So who knows? Maybe the Arctic is getting more clouds, and because of the increase in evaporation, and if that's the case, well, it might actually be a negative feedback. If we really will anticipate a reduction in continental ice and snow cover, would result in positive feedback. That's quite likely, more likely positive feedback. Vegetation changes can cause a feedback effect. Since vegetation tends to be darker than dry soil, a reduction in vegetation cover would tend to make the surface more reflective. That would be a negative feedback. So actually, if you have, let's say, less vegetation, curiously enough, well, it could be, you get less vegetation in a semi-desert area, well, that could actually increase the amount of reflection, but it also means there might be less clouds, and that could work the other way. Are you confused? Is this confusing? It should be confusing because it confuses me, and I think it confuses everybody. And I say that a little bit of a joke, but seriously, this is, you can see that every time you look at there's interrelated, there's a lot of interrelationships, it's very, very complicated. And as I say, we know for sure the impact of carbon dioxide, and we have some ideas. It seems reasonable that the water vapor feedback, the feedback effect of increasing water vapor is very powerful, and that it should have a net positive feedback. And the evidence is that very well could be the case, but there's so many other complications that make this more complicated. I also want to point out vegetation changes over time, so this is a feedback effect that can take a longer time, decades or probably more on the order of decades for that feedback effect. Carbon cycle, it's thought that a change in atmospheric CO2 would tend to have a feedback effect, since it would change the sources and sinks of carbon dioxide and methane. But that's going to take thousands of years. And I don't think anybody has any idea what feedback effect that would be. The instantaneous response, changes in water vapor, lapse rate, clouds, and ice, still cover, that happen immediately or quickly. Changes in vegetation take longer, and as I mentioned. Climate sensitivity. This is the big question. Climate sensitivity is the question that you should, if anybody talks about climate change, what you want to ask them is, what do you think climate sensitivity is? Because nothing else matters. Everything else happens as a result of climate sensitivity. If somebody cannot talk about climate sensitivity, then they don't know what they're talking about when they talk about it. If they say that they know something about the climate, but they can't say anything about climate sensitivity, then they don't know what they're talking about. That's the thing you want to take from this, is that if you ever ask anybody, because we're not experts, but you ask people that claim either to be experts or to claim that they have some insight and that people should do something as a result of what supposedly what scientists say, well then ask them, what do you think climate sensitivity is? And why do you think that? That's important. If you have a policymaker that says, we have to do da-da-da-da-da because it's, well, what do you think the climate sensitivity is? That you have to understand that issue, because if they don't understand that issue, then they are not asking the right questions of the scientists. So climate sensitivity is the ratio of steady state change in the annual and mean surface air temperature to the global and mean radiative forcing. What that means is how the steady state, that means equilibrium change. There's a change in the radiative forcing. Radiative forcing means the amount of radiation that's reaching the surface. The amount of both total shortwave from incident solar radiation and long-wave radiations through the greenhouse effect that reaches the Earth's surface. And what is the steady state change? What is the total equilibrium change? When we talk about climate sensitivity, we're referring to the instantaneous changes that come as a result of changes in atmospheric CO2 and the ultimate equilibrium result of feedback effects resulting from these instantaneous changes. So we're talking about cloud cover, we're talking about water vapor, we're talking about ice and snow cover. We're not talking about necessarily about vegetation change. That can be a longer impact. We're not talking about the change in the carbon cycle. These are a little bit more complicated. So this is what we're talking about, are these instantaneous changes. And climate sensitivity is believed to be at approximately a constant for small levels of radiative forcing. So that is that if you double the amount of radiative forcing, then it should have approximately double the effect on climate sensitivity when you're talking about radiative forcing. As a result, if we know the climate sensitivity, the steady state global mean temperature response can be scaled up or down as the magnitude of the forcing changes. So that climate sensitivity is based on feedbacks. That's the point. And all the point is, when we talk about climate sensitivity, we're talking about the feedback effect. We know what the direct effect is, or we have a pretty good idea. Pretty good idea is roughly 1 degree Celsius. It could be 0.9, 1, 1.1. That's not a big deal. The big deal is the feedbacks which add or subtract from that initial change in radiative forcing. As we said, a doubling of CO2 should produce roughly, and I'll just write that down, just to remind you, 3.75 watts per meter squared increase in solar radiation, in radiation reaching the Earth's surface. So 3.75 watts per meter squared, and we think that that's the change in the radiative forcing, and we think that the lambda is about 3.75 watts per meter squared. And so that is the change in temperature is about equal to 1 degree. That's the direct effect. So that's what we think. The feedbacks, this is what we think this value is. So that's based on the feedbacks. Now I'm going to talk about the assessing of climate sensitivity. And this is the way that we figure out that scientists are working on this. And this is the big problem. This is the big issue. You're going to read a lot of articles about climate change, but really the ones you want to focus on are the ones that talk about climate sensitivity. The rest of it is just what they call, it's just clickbait to get people to read articles. This is the real, these are the articles that you want to read. And if you want to look at scientific papers, these are the papers you want to focus on, because we don't have a lot of time to focus on. This is what you want to focus on. The climate sensitivity can be assessed in 3 ways: by simulations using 3D atmospheric general circulation models, they're called AGCMs, or GCMs, general circulation model, through analysis of paleoclimate data. That's data from geology, from evidence from geology, from ice core samples, and from geology. So fossils, from the Earth's record, and from ice, ice core, ice cores. So, and through analysis of historical climate data. Our historical climate data is very limited. We've only had historical climate data that's really good data for less than 140 years now. Since about 1880. There's climate data before that, and there's reconstructions of the Earth's average anomaly that go back to 1850. The further back you go, the more difficult it gets to, it's more uncertain. From about 1880, it's reasonable, but that's only 140 years. That's nothing. Our historical record is nothing. And even that, even the historical climate data that we have is full of noise. It's full of noise. It's full of, its coverage is uneven on the Earth's surface. Most of the Earth's surface is ocean water. We don't have data. We did not have data on ocean surface temperatures worldwide until the last 10, 15 years on a reasonable basis. So the historical climate data is, it's a bit noisy. There's a lot of noise in the data. So we've got noisy data. We've got kind of fossil record, which is going to be very noisy. And then we've got models. We're using this is very precise ways to try to measure. But this is all we have. This isn't like having if you're a physicist, you've got a collider that you can precisely measure. You can run experiments and make very precise measures down to incredibly precise ways to measure things. We can measure gravitational waves that come from galaxies and astronomical events far, far outside of our own galaxy, because of incredible understanding that we have at the subatomic level. But measuring this is very difficult. That's much easier for us to measure an event that took place 1 billion years ago, 1 billion light years away, now than it is to understand what's going on in our own atmosphere. Biggest use is the 3D atmospheric general circulation models. These are the most important use in climate. A central core of climate science today are these what are called three-dimensional ACGMs. And what I mean by three-dimensional, we mean that we're modeling at the Earth's surface, and we're modeling the atmosphere, and we're modeling the oceans. And when it's done by grids, these are like cubes. They're grids. And what you're doing is you're simulating the atmospheric process and the ocean process at each point, and within each of these each of these cubes. So within each of these cubes, you're making a simulation that's talking about the amount of cloud cover, the temperature, the flow, the flow of heat between them. The incoming solar radiation, the effect of water underneath, the effect of sea ice, the amount, all these vary, the formation of precipitation. You're basically creating a model, you're modeling the Earth's climate. And typically, so this is, so any grid cell, so you take one of these cells, it interacts, it's basically a simulation that interacts with its vertical and horizontal neighbors through a commuter simulation that's designed to estimate the effect of long-term changes in surface temperatures to changes in radiative forcing. So that's what this is, that's what it's designed to do. Say, what's the impact, say, here in the upper atmosphere, and you're going to be simulating what's going on there, and how is heat coming from the surface, or incoming solar radiation, how is clouds changing. That's an attempt to model and simulate that. And it is done so we've noted the here is the you have what's called let me go back here. The smaller the cube, the more accurate the model. You can think the smaller cube, the more accurate the model, because you're more accurately saying what's going on. What you'd want is a model that was as small as possible, that you could actually analyze, say, the formation of clouds, precipitation, all of that. The problem is that these are enormously complicated. This is an enormously complex simulation, and it requires supercomputers to run them. Some of the world's fastest supercomputers are used to run these simulations, and billions of dollars are being spent on them. But the problem is that when you have a cube, the typical size of a cube, it can be 1 to 5 degrees in longitude and latitude. Well, 1 to 5 degrees, even 1 degree that's a big. It's like 100, I think more than 100 kilometers. It's like 100 kilometers on a square. So you got, and I think maybe you can get a little bit smaller now. But the problem is that within that you're assuming it's just a point. It's like a point analysis. So if you can think of an area that large, just think about the last time you flew on a plane, and an area that might be 25, 50 kilometers as you're passing through. There's clouds everywhere, different clouds, there's all kinds of stuff going on. This is an incredible, even the most sophisticated models are incredible simplification of reality. You're talking about an incredible simplification of reality with these models. As I've said, we talked about the required temperature change needed to restore the radiative balance. That's this. We're talking about this, and that's in the absence of feedbacks. That's what this is. That means it's in the absence of feedbacks. That's what that's what these values are. But that's assumed. That's the lambda. So that is the value of lambda here. That's the value of lambda without feedbacks. And that is the effect that's the ultimate effect, and that's the value you want to know. That's the value you want to know. So interestingly, McHarvey says the only models with the potential to reliably simulate the individual feedback processes are three-dimensional AGCMs with a high spatial resolution and a diurnal cycle. So you're actually creating where it's day and night, and it goes day and night, and for years and years. So that's how you run these simulations. So the smaller the size of the cell, the potentially more accurate, but the resolution, the more intense the computations. Very, very complicated stuff. As I say, the movement of water vapor, the development of clouds, and the precipitation of rain and snow are extremely complex, and they can only very, very, very approximately model. Cloud properties, you have to simulate, in these simulations, you have to simulate cloud properties and processes. Liquid and ice water content, mean water droplet or crystal size and size distribution, cloud thickness, the diffusion of cloud moisture from an organized circuit into the general atmosphere, and the formation of precipitation. You have to simulate all that. You're taking all that's happening in a big area and you're reducing that down to an equation at a point, for a point. That's basically what you're doing. These are treated, as I say, it's treated in an incredibly simplified manner. Some models have dealt this in the past, because it's so complicated, by using what's called a clear sky model. And that's what was done more, I think, before 2000. According to this textbook that I've been using for this lecture, Harvey suggested the lower limit of water vapor feedback is approximately 0.5 degrees Celsius, suggested the lower limit of climate sensitivity is about 0.5%. So 0.5% of climate sensitivity would mean you could get to 1, so to get 1.5, you just do the calculations, what, about 3? 2.5. Yeah, that would mean that the lambda is 2.5. 2.5 would be 1 point. Yeah, right. 2.5 would be 1.5. So if lambda were 2.5, then there would be an increase of 1.5 degrees. So that would be if that's the lower limit. So the lower limit is that would be the upper limit on lambda. That with feedbacks. So this would be as high as lambda could be, would be about 2.5. Now, the statement that he concludes in the chapter in the textbook, he says that the estimated global mean equilibrium climate sensitivity from a doubling of atmospheric CO2 ranges between 2.1 degrees Celsius and 4.8 degrees Celsius. In other words, that lambda is actually, that's the belief is that, and based on the AGCM modeling, that's the case. So that's even though the textbook I'm using is about 15 years old, nothing much has changed. This is kind of still the same. The interesting thing is that people come up with numbers, but they still keep on coming up with kind of the same numbers in that area. As I say, the paleoclimate data is interesting because we talked again, this is the ratio, the temperature change is the radiator forcing to lambda, which is the climate sensitivity. Well then you just, if you can get data on the radiator forcing, which means the amount of carbon dioxide in the atmosphere, you can get some evidence of that, and the temperature, if you can get data on that, let's say old data, not historical data, but old data on, and the reason why you can do this is because these processes can take a long time. If it takes a long time, you'd have to get data over a long period, and we don't have historical data is too short. So you can use this kind of data from the ice ages or data from the fossil records. That are used to make this estimation of the climate sensitivity, this lambda. So you can get data on the radiator forcing, the temperature to make that estimation. And according to Harvey, the analysis using this approach estimated climate sensitivity ranges between 1.4 and 3.2 degrees Celsius. It's a lower estimation. And then you have historical data. And the historical data analysis using this approach estimate the climate sensitivity ranges between 1 degree Celsius and 3 degrees Celsius. So, which basically says it's possible to look at the climate data and think that there's no feedback effect. The feedback effect's basically zero. Some people think it's 3 degrees. One of what's been done, you have all these three approaches. There's a lot of uncertainty. So people's guess is that, and this has not changed. Pretty much the mainstream belief is that it's between 2 and 3 degrees of doubling. The climate sensitivity is about between 2 and 3 degrees. That's with the most likely being 2.5 degrees. So that's what we're going to see is, that's kind of the mainstream view. Now, 2 degrees, it's thought that 2 degrees is a lower limit on where you're going to have significant impacts. on the Earth's climate system. That's at least in terms of affecting human life on the planet. So that's the thing. People have been concerned about holding that increase to below 2 degrees. If it is somewhere between, say, 2.5, 3, well, then you'd have to really be concerned, or maybe you have to be concerned. That could cause more ice melt. It's going to increase say 100 years from now, 200 years from now, the oceans are going to be rising. People are going to have to adjust to that as a result of the increase in temperature. That's the thought there. But if it's lower, let's say it's 2 degrees or below 2 degrees, well, maybe there's a lot less that needs to be done. And that's the big question. That's the big question here. What's the amount that needs to be done? That's why people aren't rushing out to do to make major changes. You're talking about the Paris Accords, you're talking, that is not a major, there's no major changes that are happening. The Paris Accord is basically something everybody can feel good about, and nobody has to do very much. But everybody feels really good, and right now that's what's important, is that people feel good. That they feel like they're doing something when in fact they're actually doing almost nothing. So, that's the reality, and that reality is because we don't know. We're because of that uncertainty. I'm going to talk a very brief, and I just want to give you a feel, and what I hope for, my thought is if you're interested in this subject, I've given you some basic background information. At least you'll have some idea of how to think about this, so when you turn to these papers, you can focus on what's important. I've told you about how the basics about how the climate works, the basics about climate sensitivity, that there's the approaches, the 3 major approaches. The papers are written from these, to discussing these approaches. So you can approach the literature, and at least with some knowledge about you can look at it and say, oh, okay, well, I learned about that and that, and this is where this paper fits in, and this is what this paper says. So that even if you can't understand the detail of it, or only superficially understand the detail, you at least have some idea. You're better informed than the average person that would never even turn to the literature. You'll at least be able to go to the literature and have some idea what's going on. So that's what I'm hoping to do here. So I'm going to talk about a 2017 paper. 2 of these were published actually in September. So these are very, very new, and they have they're opposite. Well, one is saying it's actually greater, the climate sensitivity is over 3, and the other one is saying, well, actually, it might be really low. This first paper is saying, gee, it's really, really high, maybe we got to do a lot. And this one is saying, well, it looks like it's kind of low, maybe we don't have to do as much, and maybe we have more time. And in between is a paper from the Paleolithic data that's in between. And that kind of reinforces this consensus. So I'll talk about them, and again, it's just going to be very brief. It's a very brief and very superficial overview. I don't want to say that it's anything other than this. This one, the slow climate mode, the title is Slow Climate Mode Reconciles Historical and Model-Based Estimates of Climate Sensitivity. What I did was I couldn't download this off the paper. Sometimes you can't download these papers off the internet, you have to pay for it. And there are a lot of these that supposedly people are talking about, but then you have to pay to get it. And so unless you have that access, and you might, if you as a student you have access to that, well that's fine. You can use that. At the present I don't, so but what I did here was the paper was and you couldn't download it in PDF form, so I took screenshots of the paper, so I could get screenshots. So that's where this came from. What this paper did was it uses 24 AGCMs, and its argument is that there is a long-term, that the effect is slow. That the effect on the climate from a change in radiative forcing takes a long time. And one of the things we've learned, and I mentioned this last time, the longer time that it takes for the adjustment to be made, the higher the increase in temperature that will be required in order to restore the balance, the radiative balance. And by radiative balance, so if you have an increase, let's say you have an increase in, let me try to make this, if this is not clear, if it's not clear, let me go back. Let's see, we'll get back to that in a moment. So go back to this, use this diagram. Say I have an increase in net radiation in the atmosphere. Then that is going to increase the amount of radiation reaching the surface. So that means now there's more radiation reaching the surface than going into space because of the change. That's what's called a perturbation. We've changed the atmosphere. So the question is, how long does it take and what is the process to where the atmosphere adjusts to that change and the amount of radiation going into space is the same as the amount of radiation reaching the surface? That's called radiative balance. When you have an increase in atmospheric CO2, that upsets that balance and increases the amount of radiation reaching the surface. Then you have to have an adjustment. The adjustment, then there's an increase in radiation from the tropopause that then eventually equals the radiation reaching the surface. That's balance and that's equilibrium. That's a new equilibrium state. So that's the question, how long does it take? And the shorter that it takes, the quicker that it takes, then generally what that means is there's a smaller adjustment, a lower increase in temperature that's required. So what this paper is saying, they're claiming it takes longer. They're claiming that instead of this straight line, that the process is some kind of straight line process, but they're saying that it actually takes more time. That this is little impact, and then an increasing impact over time. So they're claiming, this paper is claiming that it's this kind of a process. It's not a linear process. It's this kind of convex curve, and that means is it takes longer, that the temperature increase is greater. So that's what the paper is arguing, and it's arguing. And I looked at this and I said, well, but what it's doing, it's just taking from ACGMs. It's running models. It's running models over more than 100-year periods, and there's around 24 different models, and it's looking at the results, and it's drawing a curve through the results of the models. Now, this is a problem. This is one of the challenges of climate scientists, of climate science, is that because it's hard to actually make real measurements, the models are basically used as data. Now, if I did that that would be like if I modeled the economy and I had individual people, and I was running a simulation model based on individual people, and I would produce, and it would be based on the 1920s, and I said that shows what actually happened, and I was running a model and saying the people did that, and they interacted that way, and it had that outcome, and therefore that's the outcome. In other words, the outcome of the model is treated as data. No, we don't do that in economics. And they typically don't, physicists don't like this either. So it's very controversial. Believe me, a lot of fields are looking at this and saying, really? I don't know. I'm personally skeptical of it, because you know that the models themselves are very rough. They're very rough models, and yet people are running these kinds of simulations and then telling us that they're proving something. Now, one of the interesting, and so I actually, this is the great thing about, I took this chart and I removed I took out all the colors and the lines just to look at it, and I can kind of, but, you know, when you look, they're saying that you have this kind of relationship, and I don't know, it kind of looks there, it looks pretty linear, I don't know. That, you know, I've done a lot of statistical analysis, it's, I don't know. They're making a big statement. Maybe may be right, I don't know. Now, what I found interesting about this paper, because at the end of it, and I found it because there was an article in the Washington Post that was written about it, and of course the article in the Washington Post said, well, we figured this out now. These models agree with the historical paleoclimate and model based, and so now it's all figured out, and we've got a massive problem. But when you go and read the paper, I'm a bit skeptical. I'm just a bit skeptical of this kind of. I mean, it's interesting. You know, it's interesting. You want to think about it. You want to think about it. But what I found interesting about. Oh, I'm sorry. I did want to point out this is done in order to compare. The idea is to compare with the paleoclimate. The paleoclimate and with the historical climate data. The effort is to reconcile those because of those differences. What I talked about earlier, the three approaches have a different outcome. Well, they're trying to reconcile those differences. So that's, I mean, it's a good idea. They're making a good idea. But what I thought was interesting about this paper is they don't make any forecasts. You know, if I write a paper in economics, and I state that something's going on, well, my purpose is to make, well, what's the forecast going to be? What are you going to say the world's going to be next year, or 2 years from now, or 5 years from now, as a result of this? And at the end of it, it's not really, they don't really say. Well, you know, how can you test? They're saying that there's some impact. They're saying it takes a certain length of time. Okay. Well, if you think it takes a certain length of time, then what's your forecast? And so that's what I find very interesting about these papers, is that they won't make a forecast. That's very interesting. They won't make if you won't make a forecast of something, if you're not willing to go on, you know, but this is what they do. This is climate science. You know, and I'm not saying they're wrong. I'm not saying they're wrong, because it's very difficult. It's a very difficult field. And I think one of the things I want you to get out of this is how complex this is. And a lot of people that criticize it don't know what they're talking about. But on the other hand, it's very easy to see how the scientists are getting very sensitive about what they know and and to admit what they really don't know. So they're in a difficult situation. I would not want to be a climate scientist any more than I would want to be president of the United States. These days, it's very difficult. Those are two jobs I wouldn't want to have. The second paper is the LGM is the last glacial maximum. So what they did was they looked at the effect of and presumably they were able to get ice cores from tropical areas on this. And the interesting thing about this paper, and I'll give you, if you're interested, the authors of this paper, it's a fellow named Hargraves and Annan, James Annan, and they're actually based in Yokohama. So this is actually work that's being done in Japan. There's of course Japanese climate scientists and Hargraves and Annan. I know Annan. I've read his work read a few of his papers over the last 10 years. You know, he's a serious, you know, these are serious climate scientists, and he's kind of mainstream, but more on the skeptical that there's a big impact. He thinks it's definitely lower. These people think it's definitely lower, and I think part of that is that being in Japan, these Americans are they're away from that kind of all the politicization, and so they're able to. I think they're a little bit more. They're in a bit of a safer position to state something like this. But so what they did was they looked at, as we said, if you can get the radiated forcing and the temperature, then you can estimate climate sensitivity. And that's what they did using the paleoclimate data. And so what they have here is they have data on tropical temperature change in the last glacial period. So they're looking at tropical temperature change, and they're looking they're looking at that data and estimating climate, as a result of estimating climate sensitivity. And these are from models, and then the red dots are data. They're observing. They're able to observe radiative forcing. It would be three-dimensional. They're observing temperature change. They're observing radiative forcing change as a result of CO2 change. So they're able to estimate the CO2 content in the atmosphere, and then they're estimating the sensitivity, climate sensitivity as a result. And what they get out of this is about 2.5. That's what Annan and Hargraves think it's about, that the climate sensitivity is about 2.5 degrees Celsius. And they think it's very unlikely over 3. So these are people that think it's not out of control. These are people that definitely think that it's not out of control. We have a problem, but it's not a massive problem. 2.5 degrees, and it's very likely to be very unlikely to be above 3 degrees. Whereas this paper says it's over 3 degrees, we got a big problem. And this paper says, this is from 2012, but this is fairly current. This paper is saying that, yeah, our analysis of this data suggests that we don't have a big problem. It's a problem. There's something that's a real problem. 2.5 degrees. It's not nothing, and it might have caused some problems, but it's not. These guys say the building's on fire, and here they're saying, well, we just have to watch, and we may have to put we may have to make some protection. We have to make some changes. This paper would be saying we've got to change right now. The world's going to die. We're all going to die, basically. And so they estimated the climate sensitivity. What they did was they took these model. These are the blue dot. The big blue dots are the model outcomes. So these are actually the ACGM, the atmospheric climate models that I presented to you earlier. So those are the outcomes of models, and then that is, and they've weighted, and what they did, they weighted it by, you can see, if you go across, that's the estimation, and based on the radiative forcing, the tropical temperature. If you do a cross-section here, that tells you the frequency. And when you go up here, there's a lower, see how there's a lower frequency? That's where that comes from. The lower frequencies up here, higher frequencies here, because the results are concentrated in that area. And so you can see that is the outcome. They weight these different ones, and this is a prior. They used what's called a Bayesian approach. They had a prior estimation, which was about a little bit over 3. And they said, okay, they made that assumption, then they challenged that, and they said, well, we think it's about, low 2s, 2 to 2.4, 2.5. And it could be, but very unlikely over 4. Very unlikely over 4. A higher probability over 3, but lower, much higher probability of being less than 3, but also very low probability of being less than 1 degree. So it says a very low probability of below 1. This is about 1.5. Low probability of being below 1.5. I think this is the consensus. I think this represents the consensus in climate science today. This is a pretty. If you go out and you'll look at mainstream climate science, I think this is the consensus. And here's the problem, and I'm going to go to this third paper. The problem is, it's called Emission Budgets and Pathways Consistent to Limiting Warming to 1.5 degrees Celsius. This came out in September, as well. The first paper I said came out in September. It didn't get I don't think it got a lot of press, but this one did. This got a lot of press. This got a lot of press because what they pointed out that something that everyone, that most people agree is true, is that the models, these models have been over-predicting warming over the last 20 years. And that's a major problem with these models, is that the models have been over-predicting the amount of observed warming over the last 15 years. That they've said 15, 20 years. They've said that the warming was going to be higher than it actually was. And this chart, what they're trying to do is they're saying, well, what is the carbon budget means how much carbon equivalent can you put in the atmosphere? How much more fossil fuels can you burn before you get a point where there's enough carbon dioxide and other greenhouse gases in the atmosphere that you're going to have at least a 1.5 degree temperature increase, with a 66% probability based on the models. So that's what that is. And you'll see this. This is the cross that shows both. This is the estimated temperature increase. That's the temperature increase since the 1861-1880 period. And this shows the total amount of anthropogenic CO2 emissions from 1870. And these are error bars. So you can see, even here, if we're talking about, we're not even sure, here's the degree of the range. It's a plus or minus about 100, let's see. I think 75, plus or minus 75. So it's a value of about 525 plus or minus 75 gigatons. Remember, gigaton is a billion tons. So gigatons of carbon. So that's what that figure, that 500 means, gigatons of carbon in the atmosphere. And remember, a gigaton is 1 billion tons. 1 billion metric tons by weight of carbon in the atmosphere that's been added. But so that's 525 plus or minus about 75. That's more than 10% plus or minus. So we don't even know this figure within 10 to plus or minus 15%. So you're trying to figure out what these impacts are, and you don't even to measure something as basic as that, we're not really even sure. I mean, we have some degree of certainty, but that's still a broad range. That's a fairly broad range of change. But the important thing, and and they pointed out in the paper, and a lot of people noticed this, is here's the model forecast. The models, this is the line, the predicted line of the models of the impact of increasing carbon in the atmosphere, and the forecasted temperature change. Here's the actual temperature change, and they're saying it's on a different trajectory. They're saying, guys, look at this. It's a gap. There's a big gap here. There's a problem. We're overestimating the temperature. So that's what's interesting about this paper. And basically what they're pointing out, and this was in the last of the IPCC, the Intergovernmental Panel on Climate Change of the UN. That's the United Nations Intergovernmental Panel on Climate Change. They put out a report every 6 years, and the last report, which was the fifth assessment, noted that out of 114 models, that between 2000 and 2014, 111 of them out of 114 were overestimating the temperature. That's pretty high. That was in the official publication. That was the official publication by the UN the last time was pointing this out. Almost all the models were overstating the temperature. Well, that should be a problem. And so what these people are saying, well, it looks like we got a problem with these models. So if there's a problem with the models, we might be overestimating the impact, and maybe we have more time and to make an adjustment. And we don't have to go out and geoengineer the atmosphere. We can get reasonable about this. We're going to have to do something, but maybe we have more time. And I think the point here is, well, maybe we also have more time for countries like India to develop, for Africa to develop. That we're not going to say, well, you don't get to develop. Why don't we all get, but you don't get to now because, you know, well, otherwise we'll all die. If you get to drive cars and have refrigerators and, you know, and nice fancy computers and play computer games like the rest of us, well, that won't work. So that's the issue. Now I'm going to talk about the something I observed, and this is when I talked about the historical record, and that some people think it could be the climate sensitivity could be very low. What I observed about 10 years ago when I first looked at this, and this was the data that I looked at, and I said, one of the things I noticed right away, and being an economist, you know, we look for cycles. As economists, we're kind of natural to look for cycles in data. And so what I did was I took the global anomaly data. That is the different, global anomaly talks about the difference, you're averaging global temperature, and you're looking at the difference between a long run average and on a monthly, let's say here on a monthly basis, the difference between that average monthly temperature and the long run average. So that's what this is. And so what I had noticed was I could see that, and I remember I didn't know what was going on. And I looked and I could see that these periods were about the same. You could see it's kind of up and down, and there's some kind of up and down that's very similar in length. And so what I did was we had, it was 2006, it was 1880, and I divided it up into 4. It looked like they were about the same. So it was about 31 years. In fact, it turned out it was 380 months. So I took periods of 380 months and I divided into 4 periods of 380 months. And I looked, I said, well, you've got, and then I did a regression on each of these. So you do a regression on these, and then you can look at the slope, the resulting slope of these lines. So that's what these lines are. It shows the slope in each of these periods. Here the slope was minus 0.2475. So minus 0.2475. Then positive 0.3491, temperature's rising, temperature's falling. Minus 0.0441, 0.5537. So you can see that's bigger, that slope is less, this slope is greater. And I thought, you know, well, that is CO2 has been increasing. Maybe what's going on is what we're seeing. There's something natural. There's something natural going on, but at the same time, there's on top of it is anthropogenic. And if you look, the increase here is 0.2, about 0.2, and the increase here is 0.2. And I also found evidence of, I found evidence in the data of, that suggested that these were real cycles. That the real cycles, I looked at monthly changes in temperature and I observed patterns of zeros and ones. I looked at patterns of zeros and ones in the data, 0 being a temperature reduction, monthly a temperature reduction, ones being a temperature increase, and I found some very interesting numerical patterns in the data that suggested to me that these were real cycles. There was some kind of underlying natural cycle. So at that time I thought, well, maybe that means that the climate sensitivity is very low. I thought it meant that it might be very low. So what I did was I said, well, if it is, and I wrote a paper and I showed some people and people thought I was crazy. So, you know, and that was 10 years ago. So I lost a friend or two actually because of it. Then I realized, well, okay, I don't think I want to do, you know, you only want to get so serious, you know, because people have very strong beliefs about this and they didn't really like to be challenged. So, at any rate, what I did was I said, well, if that's the case, I said, well, if these are lengths of 31 years, 380 months, then we're actually entering a new era, and that the temperature increase should be relatively flat. Now that's what I told people that I know. I said, well, I'm forecasting, 2007, I said, I'm forecasting that the Earth's temperature is going to stay relatively flat. And actually, they did for about seven or 8 years. It did exactly what I expected, almost exactly what I expected. But we'll go and see where it's changed. And here's the change that I've added up to 2017, and I'll give some detail. See, fall, and now positive. I expected the slope to be a little bit positive. But now it looks very positive. Okay, but now we're going to look more deeply at that. And it is, and this was, when I gave this lecture a year ago, this is the situation. This is the situation a year ago. And you can see that up to early 2014, so late 2006 to 20, so the 8-year period, the temperature, it was flat. It just as I forecasted, it was absolutely flat. And then we had a very massive, what's called an ENSO, the equatorial north-south oscillation that is known, that we know as El Nino and La Nina. If you El Nino, that's actually the scientific name for that is ENSO, the equatorial north-south oscillation. So so we had that event, and at that time the temperatures were starting to come down. The question was what was going to happen. Well, the interesting thing is that they have kind of come down, and they went up a little bit, but now they're coming down, and it's kind of getting close to this line now, but it's still a little bit above that line. So in other words, I don't know. It's like everything else, I don't know if my forecast is going to be right, but what's telling me is that, well, I might not have been right either. And that's okay. You know, if you have new data, you want to look at that and say, you know, what's right. Here's the slope. Here's the slope for the whole period. Here's the slope for the first part. But this is heading back. It's kind of heading back down now. The question is, so here's the thing you want to watch for. And if there's anything, if you're interested in this, the one thing you could do, all you have to do is get online, and there's several sites. I can give you those links. I think I have that here, but if not, I'll make sure I put that in. I download the data on a monthly basis. I look at the data on a monthly basis. Every month, towards the end of the month, they come out with the updated numbers on the global temperature, and I look it up. There's 2 sites that I use. I use one from the National Oceanic Atmospheric Administration, and then the other one is one that's run by Berkeley, by a physicist at Berkeley University. It's an alternate, interesting approach. I think they're both valid ways to look. It's kind of I use it kind of a check on the NOAA, but the results are fairly similar. So I check those on a monthly basis. So I'm kind of monitoring to see what's happening, and it's because it's very interesting. And I think that over the next 10 years, I think the answer is we're going to have a real clear idea in 10 years. In 10 years, if it goes back to this line, and we have something like that, keep an eye on this. My forecast is that, on my forecast, it's going to go back to this, and that we're going to have some kind of, which is going to say that we have some kind of temperature, and that my guess is that the climate sensitivity is somewhere between 1.5 degrees Celsius and 2 degrees Celsius. That's what I would guess. In other words, that a doubling would produce that. If that's the case, then India basically if that's the case, India can go forward and develop. Africa can develop. China already developed. God bless them. They already developed. And as I said, China, what I see is that China's discovery of climate, a religion, has to do with China's self-interest. They've got their electricity, and if India doesn't get it, well, that's their problem. That's probably better for China. So So keep an eye out on that. And you can say 10 years from now, I remember that guy said, was he right or wrong? At least you left something, if it's fairly flat, you'll say, you know, that guy was right, he was right, it probably is low. It might well be low. And if 10 years from now it turns out relatively flat, then I assure you that the discussion, the current discussion, it's all going to change. It's all going to change, and people are going to question these models, and they're going to say, well, maybe it's sensitivity is lower. If it's somewhere like this, if it is something like that, then we're going to have to make major changes. That 10 years from now, we're going to probably have to make major changes if it keeps up in that. And I think the answer is, or the point is, the next 10 years are crucial. The next 10 years are very crucial towards this. And that way, we need now to look at, well, who's emitting carbon dioxide? If you need to make a change, what do you need to do about that? Let's see, we have 5 more minutes. We have 5 more minutes. So I think I'll just introduce this topic, and I'll go over this. And I think this is for you're probably interested in this. So this data is directly of interest to you. I'm going to see if there's an update on this. This is through 2014. And you can see this is the metric ton CO2 output equivalent of greenhouse gas output. And so this tells us who's emitting and where the change is. I have this in, it's the log, this is a logarithmic function, so I did it in a log function so that, to make it easier to put on a chart like this. And you can see, the first thing you can see from 2000 to 2014, Asia and Oceania, East and primarily East Asia, the equivalent of 10,500 metric tons and to 17,300. The biggest increase was in Asia, and it's mostly China. North America, you can see it actually fell. Europe fell. These actual declines, very aggressive, both the United States and especially Europe, very aggressive efforts to reduce, to have alternative energy sources, and also the effect of the financial crisis and the slowing of economic growth in Europe and America has had an impact. But we've seen also an increase in Africa, a bit of an increase in Africa, and a fairly large increase in the Middle East. Middle East is developing. Of course, they have lots of fossil fuels, and at least until very recently, a country like Saudi Arabia with lots of sun, how much output of solar power do you think Saudi Arabia had until very recently? Zero. So, well, there are a lot of changes. It's very interesting. It's very interesting what's going on there. In Saudi Arabia, been reading some stuff. I was reading about how they said the 10th richest man in the world, they basically tortured him. They hung him upside down and tortured him. It's really, fascinating changes that are going on in this country. And I think it's because they realized, look, this could be happening, you know, from climate change, and that they really have to change their economy and society. At any rate, so that's the big picture, and we can see, you can estimate the direct effect, that direct effect that we talked about, in degrees Celsius over the last the last 15 years. The direct effect is about 1/10 of a degree Celsius. So the increase in global temperature is about 1/10 of a degree Celsius over the last 15 years as a result of the increase in carbon dioxide output, and almost all of that, or the majority of that, about 0.4 degrees, is from East Asia, is from Asia, primarily China. As I say, I want to talk about electricity. I think it's it's the biggest single sector. The total global emissions is electricity is the large, 36.6%. Then we have these other effects: agriculture, transport, residential, other fuel combustion, industrial, construction, manufacturing. But the big emitter, biggest single emitter is electricity. And so that's A, I'm going to focus on that, and B, of course, I talked about the importance of electricity in economic growth and development. So we're going to focus on that. The increase, what's interesting is that the increase in total global emissions in 2000 to 2010, over that 10-year period, almost half of that was from electric power generation. So on the margin, electrical generation is the big contributor. And so when you're talking about the development, for example, of India now, India would it would develop through a big increase in carbon dioxide output. It's definitely if India develops anywhere the way China's developed over the last 15 years, India's going to. This is now going to be India on the margin. So you can see that big impact. Less industrial construction, manufacturing, everything else kind of. A lot smaller. There's the big one right there, is electrical power generation on the margin. So then what I'm going to do is kind of go, now I'm going to focus on global electricity generation. And the output in 2000, this was terawatt hours, 14,720. Coal 38% globally. Coal 38, the biggest, so that's the biggest. Coal, gas 17.7, oil 7, nuclear 16.6, about 1/6, hydro about 1/6. There's renewables, 2.2. And here's the big chain, and renewables breaks up into and most of that is biomass. That's like burning, that's not necessarily it may not be environmentally friendly. And then that's the change. It went up to 6.7% in 2014. But coal, notice the big change in coal. Do you notice the big reduction in the use of coal? I don't either. I didn't notice that either. So it's very interesting. Over that period, the use of coal increased. And if India develops, the use of coal is going to continue. It won't drop. So we'll leave it at that. We're going to go over this, but you'll get this. We'll be going over this in the next lecture. I know that you want to talk. You want to talk about your topic, and I do want to go over that. I got from you. Thank you for that. From now on, folks, I want every week before the class an update on your project. I want an update every week, and I'm going to stick to that. That is, and thank you for that. So I'll make that very clear. I want you to do that. I want you to get on this and be thinking about it, and rather than rushing the last minute to do something. I think you can do. All of your capable doing some very good work. So thank you. We'll go over that, and you want to talk about that. And I'll be going. It's in 07. That 17th, 607. I'll be in that classroom in just a couple of minutes. Thank you.